This lecture is about logarithmic functions. The material in this lecture corresponds to section 5.4 in the textbook. We begin by considering the exponential function, a function that we've been looking at recently. We see that it is of the form f of x is equal to a raised to the x power. On the right is a graph of y, or f of x, is equal to 2 raised to the x power. We can see certain characteristics of the function from the graph. It is an increasing function. Okay? As x gets larger and larger, f of x gets larger and larger. We also see that it passes the horizontal line test. This means that it's a one-to-one function, and as such, it has an inverse function that we can take, f of minus 1 of x. For the exponential function, the inverse function is something that we've defined to be called the logarithmic function. When we have an exponential function, y is equal to a to the x power, the way that we get the inverse function, in this case the logarithmic function, is by replacing x with y in the function that we're starting with, in this case the exponential function. And when we do that, we get x is equal to a to the y power. And this is an implicit definition of the inverse function. The way that we get the explicit definition is by taking that equation and manipulating it so that we have y alone on one side of the equation. And when we write it that way, explicitly, it's defined as y is equal to log base a of x. This is what we call the logarithmic function, and that's the usual way that we write it. There are some restrictions on what the various elements of the equation can be. A has to be greater than 0, and we don't include cases where a is equal to 1. They're not meaningful. We also insist that x, the argument of this function, has to be positive. We can work with logarithmic functions. We can take the expressions and we can manipulate them and we can figure out things we don't know. So, for example, if we have 1.2 and we cube it, we raise it to the third power, and we say that that's equal to m, we can write it using the logarithmic representation by saying this is the same as log of base 1.2 of m is equal to 3. Similarly, if we have e raised to the b power and we know that it equals 9, we can write this as log base e of 9 is equal to b. Here's another example. When we have log base q of 4 equals 5, this is equivalent to writing q to the 5th power is equal to 4. We can use the logarithm to help us find certain things, like, involving exponential functions. So if we have log base 2 of 16 equals y, and we'd like to know what y is, all we have to remember is that this is equivalent to 2 to the y is equal to 16. And we can solve for y. We keep in mind that 16 is equal to 2 raised to the 4th power, so this means that y is equal to 4. Let's go back and look now at the graph of y is equal to 2 to the x. Now, if we keep in mind that this is a graph of the exponential function, we can see, just looking at the graph, that the domain, that is the possible values that x can take on in this function, is any real number. If you look at the horizontal axis, you see that x can be anything. The arrows indicate that the x value goes off to minus infinity to the left and up to infinity on the right. The range, on the other hand, is what the function can take on. F of x, the values have to be all positive. This graph is entirely above the x-axis. When we're looking at the logarithmic function, when we keep in mind that it's the inverse function of the exponential function, we recall that we can take the domain and range of the function that we're working from, in this case, as I say, the exponential function, and just swap them to get the domain and range of the inverse function. So what this is going to mean is the exponential function, which we saw in the last slide, in that function, the domain is the real numbers and the range is y, such that y has to be positive. So for the logarithmic function, the inverse function, the domain is going to be, well, x has to be positive and the range is the real numbers. Now, when we're looking at a particular logarithmic function, say capital F of x is equal to log base 2 of x plus 3, and we're trying to figure out what the domain is, we have to keep in mind that the function argument, what's in the parentheses, the value that we basically feed to the log function, has to be positive. So this tells us that x plus 3 has to be positive. And that means that the domain of this function, the values that x can take on, are x, any x value that's greater than minus 3. If we have a more complicated function like g of x in this case, which is log base 5 of a ratio, in the numerator 1 plus x, in the denominator 1 minus x, then we have to keep in mind that again the argument for the function has to be positive. So that means that 1 plus x divided by 1 minus x has to be greater than 0. Now, there are two ways that this can be true. One way is that the numerator of this fraction has to be positive, and at the same time, the denominator has to be positive, so that we have a positive number over a positive number, and that is going to be positive. Okay? The other possibility is that the numerator can be negative, but if it is, then the denominator must also be negative. And if that's the case, we'll have a negative number over a negative number, and that ratio will be a positive number. So either of these conditions will satisfy the requirement that the function argument be positive. So let's look at the one in blue, the one on the left first, where both the numerator and the denominator have to be positive. In that case, we see that x, based on the numerator requirements, is greater than minus 1, and then for the denominator, x is less than 1. Okay? So if x is greater than minus 1 and x is less than 1, those values of x will satisfy the requirement that the function argument be positive, based on the constraints in blue. And that we can rewrite as x has to be between minus 1 and 1. Okay, so that's fine. Okay. Any value of x between those will work. Now, if we consider the constraints on the right, where both the numerator and the denominator of the function argument have to be negative, and we start simplifying, we say, okay, let's look at the first one. For the numerator, 1 plus x has to be less than 0. In order for that to be true, then x would have to be less than minus 1. And then for the denominator, in order for 1 minus x to be less than 0, x would have to be greater than 1. So at the same time, x would need to be less than minus 1 and greater than 1. And that's not possible. There is no value of x for which that's true. So that means, since it's not possible, the only valid domain is the one that's given by the constraints that were originally listed in blue on the left, where both the numerator and the denominator are positive. And that domain corresponds to x such that x is between minus 1 and 1. So now let's look at the graph of a logarithmic function. We had already looked at the graph of the exponential function. Okay? And here we have the exponential function in blue, its graph, y is equal to a to the x. It's plotted here, and then the inverse function, y is equal to log base a of x, is graphed in red. And then the axis of symmetry, y equals x, is graphed here as well. And you can see that y is equal to log base a of x is the mirror image of the exponential function. Y is going to equal log a of x if and only if x is equal to a to the y. And when you say if and only if, it means that both conditions have to be true. And we could write the statements in either order. We could also say x is equal a to the y if and only if y is equal to log base a of x. Now, the graph on the left is the case where a, the base, is greater than 1. If the base instead is a fraction, say a half or a third or something like that, and it's between 0 and 1, the graphs are going to look different. We see the exponential function drawn here in blue on the right, and the logarithmic function drawn in red. And again, the axis of symmetry is y is equal to x. So we have the red graph, the inverse function, is still the mirror image of the blue graph. It just looks different, but the same conditions hold true. There are things that are a little different, and this is a slide that I invite you to look at more closely. You know, after you go through this, you might want to go back and look at this again when you're doing problems, because this one really kind of shows what's true for both cases, where it doesn't really matter what alpha is. You still have the same characteristics of the log function and the exponential function, and then where they differ. You can get a sense of that by looking at this more carefully. Now, there are some properties of the logarithmic function that are going to hold true, and I want to talk about these a little bit. Now, the graph that I posted here is the case where alpha is greater than 1. First of all, it is true that the domain of the function, the log function, which is graphed here in red, is going to be x is greater than 0, and you can see that. There is no value of the log function that is left of the vertical axis. The range is any real number. Okay, and again, it's pretty clear that the vertical component of the graph can be any number. It can be all the way from minus infinity to infinity. Okay. The second thing is that we see that there is an x-intercept. It's at 1, 0, and that there is no y-intercept. The y-axis actually, the y-axis actually acts as an asymptote for the function y is equal to log a of x. The third characteristic or property of the logarithmic function is, well, as I said, the vertical asymptote. I got a little ahead of myself there, sorry. The fourth is that we can see that f of x is increasing if a is greater than 1, and that's what we have graphed here. If you look back at the previous slide, you'll see that the function is decreasing everywhere if the base is between 0 and 1. The graph of the log of base a of x contains the points 1, 0. They all do. Okay, and then they all contain the points a, 1, whatever the base is. Okay, and then the point 1 over a, minus 1. And then putting in those 3 points really helps with sketching the function. Just plop those in, and then it's not too difficult to just sketch the function in. We also see that the graph is smooth and continuous. Now let's talk a little bit about the natural logarithm function. We already talked about the case where we have Euler's constant e as the base, when we have an exponential function where we have e is equal to x is equal to e to the y. The inverse function of x is equal to e to the y is called the natural log function, and it's graphed here, and basically it's the log base e of x. So we have the exponential function graphed in blue, and then the log function, the natural log, graphed right after it in red. And it's called the natural log because it's based on e, which is a variable that is seen in nature. There are many natural systems and phenomena in nature that when we model them, we end up using e to describe what's going on. And the same is true for the natural log. Graphing a logarithmic function. So graphing a basic logarithmic function is not that difficult because, as I mentioned before, we find the 3 points that are going to be in there, and then we just sketch in the curve. But sometimes we'll have a function that is a transformation of one of the natural log functions, and we have to figure out how we're going to graph it. So when we did graphing of this type before, when we had other functions, we would usually begin with a basic function, and that's what we're going to do here. Our goal is to graph f of x is equal to minus the natural log of x minus 2. In order to do that, we're going to begin by graphing the canonical underlying function, y is equal to the natural log of x. And so that means sketching in the 3 points. The natural log of x is log base e. So the 3 points we sketch in are 1, 0, which is something we're going to sketch for every logarithmic function. Okay, and then the other points that we put in are 1 over the base, which in this case is e, comma -1, which we graphed here. And then we have the third point is the base, comma 1. So we put the 3 points in, and then we draw the curve between them. That's the canonical function, y is equal to the natural log of x. Then we do a transformation. The next step is to take the function and multiply it by -1, and that's effectively rotating it or reflecting it about the horizontal axis. So that means we take it and flip it over that axis, and we wind up with, again, the point 1, 0, which doesn't move. And then the other two points that we had sketched in are going to flip. 1, 0 doesn't move because it's right on the axis that we're rotating around. But then we have this point 1, e, 1 over e, comma -1 is going to be flipped up to 1 over e, comma 1. And then we also sketch in e, comma -1 instead of e, comma 1. And now we have this graph. We don't have the function yet. To get the function, we're going to need to do a horizontal shift where we replace x with x minus 2. And that means moving the entire graph to the right by 2 units. And this means that instead of having x equals 0 as the vertical asymptote, we now have x equals 2 as the vertical asymptote. So then we sketch it in as is seen. So this process is very similar to the kinds of transformations that we've already done for other kinds of functions. Now, we may want to take a logarithmic function and find its inverse. So there's a process for doing that algebraically. So we'll just take the function that we just graphed and say, okay, now if we consider this to be the function, what is its inverse? How are we going to do that? So the function is written here, y is equal to minus natural log of x minus 2. And in order to take the inverse, the first step is to replace every y with x and every x with y. And so we do that, and that's marked in blue. Now we have an implicit definition of the inverse function. X is equal to minus the natural log of y minus 2. And if that's all we needed was an implicit definition, we could stop right there. But generally speaking, we don't want to stop right there because it's not that helpful for graphing or working with to just leave it like that. So we go a little further. What we really want to do is get y alone on one side of the equation. So the first step in doing that is to multiply both sides of the equation by -1. And then once we've done that, we have minus x is equal to the natural log of y minus 2. The next step is to take the inverse function on both sides because we're trying to get at that y and get it alone, but it's locked up as an argument of the natural log. So to get at it, we will take the exponential of both sides. Performing the inverse function means taking the exponential. It's the inverse function to taking the log. When I take the inverse function on the right, that means I'm taking that natural log of y minus 2, and I'm calling it the exponent. I'm saying it's e to the natural log of y minus 2. And when I do that, I wind up with y minus 2 alone. And on the left, since I have to do exactly the same thing, I now have e to the minus x. So I've taken the exponential on both sides of the equation. I still need to get y alone, but I'm much closer to it than I was before. To get y alone, I add 2 to both sides. And now I have y alone on the right side of the equation, and on the left side I have e to the minus x plus 2. And that is equal to the inverse function of the function I began with. So I graphed the logarithmic function before using transformations, and that's in blue. You can see that it has x equals 2 as an asymptote, a vertical asymptote. The inverse function, e to the minus x plus 2, is graphed in red. You can see here that it also has an asymptote. In this case, its asymptote is y equals 2. And again, because these functions are inverses of each other, the axis of symmetry is y is equal to x. Now we want to talk about what's called the common logarithmic function. If you look at a calculator, you'll see that it will typically have a button on it that's marked log. It might be marked log 10, but oftentimes it's just marked log. And that does mean log base 10. And that's because log base 10 is a very frequently used log system or group of values that are used to deal with very large numbers. It's kind of like dealing with scientific notation where you have powers, okay? Where you'll say, I'm interested in Avogadro's number, okay? 6.02 times 10 to the 23rd, right? Well, it's useful to look at anything that's based powers of 10. The metric system is based on powers of 10. So log base 10 is used a lot, and it's called the common logarithmic function. So if you see an equation that has just the word log in it with no base, that means that it's log base 10. Now, solving logarithmic equations, as I mentioned before, when we write y is equal to log base a of x, that's the same as a to the y is equal to x. Now, if we have an equation, say it's a little more complicated, let's say we have log base 3 of 4x minus 7 is equal to 2. We'd like to solve for x. And we can do that by using the fact that, a to the y is equal to x to help us. And so that means taking apart the log function and rewriting it so that we have an equation that's more readily solvable. The log expression can be rewritten so that we have 3 squared is equal to 4x minus 7. And then we can just solve for x by adding 7 to both sides, and then we see that x is equal to 4. Okay, that was a straightforward example. Sometimes we have things that are a little more complicated. So let's say we have a situation where we have log base x of 64 is equal to 2, and we want to know what the base is in order for this statement to be true. So that can be written as x squared is equal to 64. But if we do that, then, okay, we need to take the square root of both sides, and that's going to mean that we get the possibility of x being either minus 8 or 8. Now that looks all fine, except we have to keep in mind that we're not allowed to have a negative base. The base has to be positive. So if that's true, then that means we have to reject minus 8 as a possible value of x and just go with 8. So let's say we have another case where we have e raised to the 2x power and it's equal to 5, and we'd like to know what x is. Well, we can take the natural log of both sides, and since that's the inverse operation of having e raised to a power, that gives us just the power on the left side. So now we have 2x. But whatever we do to the left, we have to do to the right. So when we take the natural log of the left side, that means we have to take the natural log of the right side. And now we have 2x is equal to natural log of 5. And x is equal to 1/2 natural log of 5. And using tables or a calculator, we see that x is equal to 0.805.